Hello everyone. This is the final video in the series of videos I've dedicated to chapter 11 of Killer and Wuthers, Chemical Structure and Reactivity and Integrated Approach. And again, a final reminder, you have a scanned copy of this chapter available on Blackboard. I've looked at reducing agents. We looked at the reaction of aldehydes and ketones with nitrogen containing compounds. In a previous video, I looked at the hydrolysis of acid derivatives. And in this final video, I'm going to be looking at the reactivity of acid derivatives, specifically or focusing specifically in acid chlorides, which is the most reactive functional group of all the acid derivatives. So this is what we call the carbonyl reactivity series, from the least reactive on this part of the scale to the most reactive one. So you've got amides, which are react slowly, they hydrolyze slowly, and they need a strong acid or alkaline conditions. Then ethers, which again is they do hydrolyze in water, but the process can be slowly, and it gets accelerated if you use an acid or a base. Acid anhydrides, which are moderately reactive, or more reactive than esters or amides, and they can hydrolyze in water without the need of an acid or a base to facilitate the reaction. And finally, you have the most reactive of all these carboxylic acid derivatives, which is the acid chlorides, which hydrolyze very rapidly in water. Acid chlorides are a particularly useful level 3 functional group because they are so reactive. And that is because of the quality of the leaving group that you have, the chloride anion. So again, going from least reactive on this part, the amides, which has a NH2 minus, which is a bad functional group, a bad leaving group. It does not leave the molecule, and when it does, it's almost always when it's protonated. The OR minus functional group, which is again not a particularly good leaving group and usually needs to be protonated, form the alcohol to be able to leave the molecule. This carboxylate anion, which is a good functional group, a good leaving group, and even better if it's protonated and it's in form of the acid. And then finally you have the chloride anion, which is an excellent leaving group because the chloride anion is perfectly stable in solution. So that determines the reactivity of those of that series of carboxylic acid derivatives. The better the leaving group, the more able is the reagent to react. This is an example of reactions of acid chlorides with esters, with water, with an alcohol, with an amine to form acid anhydrides, carboxylic acids, esters, and amides. Acid chlorides are so reactive that typically, although there are some of them that you can buy commercially and they are reasonably stable, you tend to form them in situ. You tend to form them as you need them before the reaction takes place because they're very reactive and especially they hydrolyze very easily. So you tend to lose them. You tend to lose the acid chloride very easily because the stable form is the carboxylic acid. And here you've got an example of how you can make them with a compound called thionyl chloride, SOCl2, to form in situ whenever you need it. In the moment the reaction is going to take place, the substitution is going to take place, you form the acid chloride. How does the nucleophilic attack of an acid chloride look like? So I'm going to give you, if you think of a nucleophile, you can think of a nucleophile with a negative charge, or you could have a nucleophile with a neutral structure. So a nucleophile with a negative charge could be, for example, an OH minus, and a nucleophile neutral could be, for example, a molecule of water. So if you imagine your acid chloride, and you make it react with a nucleophile, and I'm going to choose the protonated version, the neutral version. The first step is the attack of the nucleophile of the carbonyl group, and the breakage of that carbon double bond oxygen, and the formation of this intermediate step. You've got the nucleophile, which will be protonated because it hasn't lost the hydrogen yet. You've got the chlorine group here, and you have an oxygen. And if this is happening in neutral or basic form, that would have there would be an oxygen with a negative charge. And then, well, this very easily can lose a hydrogen ion to form a neutral form of this, for the nucleophile to lose this hydrogen. So you've got the oxygen with a negative charge and your nucleophile that is now in the molecule, and then very easily this oxygen double bond carbon reforms, and the chloride anion is an excellent leaving group, and the new compound is formed with a carbonyl group with a new nucleophile in the structure and the chloride anion that stays in solution. And the reaction is, because the acid chloride is so reactive, the reaction happens quite easily and in reasonably mild conditions. So now I'm going to ask you to stop the video and, following the suggestions I mentioned in the previous slide, come up with a mechanism of this formation of an acid hydride. And so you are aiming for a compound of this type, the formation of an acid hydride from an acid chloride. Hopefully you stopped the video and had a go at the reaction. So what would I do? Again, remember, you're attacking the partial positive charge of that carbon in the carbonyl group by this oxygen with a negative charge, this nucleophile. So there is this breaking of the carbon double bond oxygen and the formation of this intermediate. You've got the R, you've got the carbon here, you've got the oxygen with a negative charge, you've got the new fragment of the compound, what you have added, that is going to give you eventually the acid hydride, and you have a chlorine group. And then, well, the chloride anion is a very good leaving group, so there is a reformation of this carbonyl group, and the removal of the chlorine atom in the form of chloride. So you end up with the carbonyl group form and this new fragment of the molecule, and you have formed an acid anhydride, and you liberate a chloride anion. This is the slide I showed you earlier, and we have done the formation of an acid anhydride. And now I'm going to ask you to stop the video and have a go at doing all those other reactions. How would you, proposing mechanisms for the formation of carboxylic acid, the formation of esters, and the formations of amides, when your starting reagent is an acid chloride and the appropriate nucleophile to form those compounds. Hopefully you stopped the video and had a go at all those nucleophilic attacks of the various fragments to an acid chloride, and in all the cases this is the general structure. Remember, always the partial positive charge of the carbon of the carbonyl group, the nucleophile attacks that carbon, and that means the breaking of that carbon double bond oxygen, and an intermediate stage with the nucleophile that, depending on the case, may or may not be protonated, depending if you're attacking with a nucleophile that has this structure, or if you're using a nucleophile that has this structure, you may or may not form this nucleophile already in the structure with a positive charge. easily that hydrogen, even if it's there, that hydrogen is easily lost, and you end up with this structure. And then again, the chloride anion is an excellent leaving group, so the carbon double bond oxygen reforms easily, and you end up with the final product and the chloride anion in solution. In a previous video, I talked about the reaction between carbonyl groups and tertiary amines, and I mentioned that the intermediate of reaction that you form wasn't stable, so the reaction did not progress. You didn't form anything. And in that video, I specifically said that that didn't mean that it was a wasted reaction, but that could be used. Tertiary amines can be used as very effective catalyst, and is something called nucleophilic catalysis. And in this case, they are used to improve a leaving group to facilitate a reaction. So this is a slide that I showed you in a previous video, and that's it. This intermediate of reaction is not particularly stable, and it reverts quite quickly to the original structure, the tertiary amine and the carbonyl group or an aldehyde or a ketone separated. However, that inability of progressing makes them good catalysts. So for example, this is an example of how one can use this tertiary amine, in this case pyridine, to react acetic anhydride with an alcohol, and you've got the alcohol here. And the first step is making the acid anhydride react to the amine, and that produces this intermediate compound, and that breaks easily around here to form this intermediate B. And you are interested in that one because, again, that's not a stable structure. It reverts quite quickly to liberate the pyridine. But instead of reacting back with the other fragment of the molecule, if there is an alcohol in the medium, it can attack that carbonyl group. It has made, because now that carbonyl group has an excellent leaving group, that pyridine, protonated pyridine, is an excellent leaving group. So you have improved, or this reaction has improved, the partial positive charge of this carbonyl group, and make it more attractive to attack by a nucleophile, like an alcohol group. There is not particularly good nucleophile to start with. So then so you end up quite easily with the intermediate steps of reaction. And in the final one, the pyridine is liberated, so it's a good it acts as a catalyst. It can go on and react with another molecule of acetic anhydride, and you have formed the final compound, which would be, well, in this case, the reaction of the alcohol that you have used and the acetic anhydride. And that would be your final product. So this is all. I hope it was useful. Thank you very much for watching. And please, if you have any questions, email me or post on the discussion board for the module. And if there are any questions, anything you are unsure and you want to raise in a future session, we will be doing this type of exercises next time we have a workshop. So thank you very much for watching.